Hello everybody and welcome back to PyTorch programming. So today we're going to talk about one of the most basic important elements of PyTorch, which are tensors. We'll be looking at the capabilities of tensors and what sort of things we can accomplish using them. So today we're going to do all the demonstrations using Jupyter Notebook on Google Colab. This is going to give us the capability to run our code on GPUs very easily over the web without any trouble. Obviously, you have limitations when you're using Google Colab, but for the purposes of our demonstration, it's going to work very well. Right, so the Jupyter Notebooks are publicly available. They'll be linked separately. You'll be able to use them very easily. So starting from what we need, obviously, we'll have to import Torch. Obviously, we're going to be using PyTorch Tensors here. We'll wait for our notebook to actually initialize. Right, now we have successfully imported Torch. We're going to be looking at tensors, and specifically we're going to be comparing PyTorch tensors with NumPy arrays. They have a lot of similar sort of capabilities. They both offer us a lot of functionalities that will make our lives easier when trying to when we're dealing with a big deep learning project. So let's start with creating a simple rank 1 tensor, and by that I mean just a vector, right? It's a one-dimensional tensor. Torch.zeros 10 is going to create a tensor of all zeros with 10 dimensions. So if we print this out and print the size of this using the size function, we should be able to see that it's a tensor, PyTorch tensor, with 10 zeros, and the size of this is of course a single vector. It's a rank 1 tensor of size 10. Now, as I said, we'll be comparing NumPy arrays with PyTorch tensors a lot, and because they offer us a lot of the same cool functionalities. For example, broadcasting is a very interesting one. Here I have a linear operation, just my x, which was a rank 1 tensor of size 10, plus 2. And we can see the output is that 2 has been added to every single element of my tensor. Here I have x plus 3 times torch.I, which is going to create like a diagonal matrix, and if we print that, you see that I have like a diagonal matrix of populated with 3s, and everything else is zeros basically, because that's what this torch.I is giving me. So broadcasting is a very helpful thing. Just as NumPy arrays offer us this functionality of broadcasting, Torch tensors also help us accomplish this. Now let's create a rank 2 tensor, which is basically a two-dimensional array, right? It's a matrix. Here we're going to create a rank 2 tensor of a normal distribution. Torch.randn is drawing samples from a normal distribution, which is a standard Gaussian, zero mean unit variance. Then let's print x and the shape of x and see what we have actually gotten here. So here you see we have a 10 by 5 matrix, and we have some positive, some negative values that are drawn from a normal distribution. We can also draw one from a uniform distribution. Here rand is just doing a uniform distribution, which is in the interval 0 and 1. So if we draw that, and then you see we have all values between 0 and 1, a two-dimensional matrix of 10 by 5. Now, another thing which Torch tensors can do, very similar to NumPy arrays, is we can try to change the dimensions, which comes in very handy as you're dynamically building your neural network and passing the tensor through. Sometimes you may have to try to change the dimensions of the data to make it do what you're looking for. So using the unsqueeze and squeeze operations, we can add or remove singleton dimensions from our tensor. Let's start by adding some dimensions. So here I have unsqueeze 0, and then unsqueeze at index 1 and 2, and then we're printing the shape of them just like we do with a NumPy array. And as we see, originally our tensor x is just a 10 by 5. Here I have added a dimension on the 0th dimension, so I have 1 by 10 by 5. On the first dimension I have 10 by 1 by 5 and 10 by 5 by 1. Note that here I actually haven't modified the shape of the tensor yet. This is not in place. If I print x.shape here, we'll see that it is just 10 by 5 still. I've just printed it if I were to unsqueeze it. PyTorch does support in-place operations. Normally in PyTorch with a lot of the operations, if you just add an underscore, you're going to get an in-place operation. So here I have x unsqueeze underscore at index 1. And then I just print x, the shape of x, and we'll see that we're getting 10 by 1 by 5. And of course, I don't have to use in-place operations. I can just use simple assignment, right? I can just say x equals x dot unsqueeze at the third dimension, and we'll see I've added another one. So this, in the previous cell, we had 10 by 1 by 5. Now we have 10 by 1 by 5 by 1. So this comes in very handy. Obviously, we can do the opposite as well. Instead of unsqueeze, we can have the squeeze operation, which will help us remove a singleton dimension. So here I have x dot squeeze the third index, and I'm trying to remove a single dimension there. So here is my dimension 0, 1, 2, 3. The third one is gone. As you see, I have now 10 by 1 by 5. This was not in place, so my actual tensor is still 10 by 1 by 5 by 1. Then we have the repeat operation, which will help us repeat data over a specific dimension. So here I have x equals x dot repeat over the 0th dimension. I'm not repeating, it's just once. Over the next one, which I have a singleton dimension here, I'm going to repeat it 3 times. Then I'm just going to not touch it again, it's 1. And then after that, 6 times. And then if we print the shape, we'll see that now we have 10 by 3 by 5 by 6. We have a 4-dimensional tensor. So manipulating tensors like this, as you see, is very easy, but it can be very, very helpful. Now, the other way PyTorch helps us with its tensors, very similar to NumPy, it supports indexing. So let's look at how we can index into these tensors. So for example, here I'm indexing into x. I'm saying x square brackets 0. Let's see what that's going to give me. So it's just going to get the first element of that. If you think about how NumPy arrays are made or PyTorch tensors are made, we're going to get a matrix of 3 by 5 by 6. And then obviously we have 10 of these, which is forming the overall matrix of 10 by 3 by 5 by 6. Similar to NumPy array, we have the colon operation, which is going to help us extract the data along specific dimensions. So if I have x colon and 0 and then print out the shape of that, you'll see that I'm getting 10 and then 5 by 6. The second element of it, I've just extracted the 0th dimension across that. Again, similar to NumPy arrays, I can get the data up to a specific index. So here I have x colon 3, meaning up to the 3rd dimension, I'm going to get everything in the first one. So instead of having a 10 by 3 by 5 by 6, now I have a 3 by 3. I've just extracted from the first dimension indices 0, 1, 2, and 3. And I can do it the other way around. Pick everything after that given index, right? So I have x 3 colon and then that shape. This, you can guess, is going to give me 7, 3, 5, 6. The overall, I have 10 along that dimension. So here, everything after the 3rd index is what I'm going to get. Another very useful operation is the view operation, is the way I'm just going to view the tensor that I have. So normally, so for example, let's look at this here. We'll have we're just going to print out the shape of our tensor x, see how many elements are in there. Numel is the number of elements, and print this information out, see what we get. So we have a tensor of 10 by 3 by 5 by 6, which has 900 elements inside it. Now I can try to view this in different ways, meaning try to change the dimensions of this, keeping the same number of elements. This can be very useful again in deep learning as you're passing your tensor through a neural network. There are situations where the shape might need to change. So here I have x.view number of elements, which means I'm just viewing it just like a single one-dimensional vector. Is going to give me a single vector of 900 dimensions, right? You see, is by just viewing it this way. Now I can do view -1, which is going to just do the same thing exactly. It's just a vector of elements in a row. As long as the number of elements match, I can try to view my tensor in any number of ways. Here I'm going to view it as a matrix of 10 by 90, which you can see I can simply do 10, 90 and then print out the shape. As long as the number of elements match, I'm going to get the right thing. Obviously, if I have, for example, 10 by 80, let me change this a little bit here, and I'm going to get error. It's not going to match anymore, right? So it's important that the actual number of elements that you have do match. If you can build that in programmatically, even better. But here, for our purposes, I just hard-coded 10 and 90 here. And then there are other things I can do where the second element of my dimension. So I had originally I had a 10 by 3. Where was it? 10 by it was a long time ago. 10 by 3 by 5 by 6. So my third index, my third dimension is gives me a 5. I can do the second index, which is my third dimension, and then -1, which is going to give me 5 by 180. So you see there are different ways of trying to view this. Now obviously how this is placed in memory, there are more advanced considerations. So if you have a contiguous one where you're actually controlling how this is placed in memory, that's for very specific requirements of certain projects that might come in handy. There are considerations to be made. Now, the tensor types are also another part of this we need to be looking at. Now, by default, all Torch tensors are of type float, and they're always on the CPU. Now, an important capability of any framework, a deep learning framework, is that it should allow us to use the GPU to accelerate our operations. One thing on Google Colab that you need to remember is that obviously in runtime, if I come here on runtime and then change runtime type, the hardware accelerator has to be GPU. Now obviously I can use none, which is just going to give me CPU, or TPU, which is Google's own thing, and it's best to avoid that unless you know exactly what you're doing. In this case, we're just using the GPU just to demonstrate this portion of this. So right now, my X tensor is a Torch float 32 type, and it is on the CPU. There is no indication that it is on the GPU now. By default, everything is on the CPU, and everything is a float. Now I can try to convert types. So here I'm going to cast my X tensor into a long, which is a 64-bit integer. And then just going to print the first element of this because the whole thing might be a bit too long. Now, right now, if we look at this, it is going to be a long tensor. So if we print x.dtype right now, and let's look at it again, it is integer 64. Now the device, as I said, by default, every tensor is on the CPU. So device.device function on the .device is going to give me whether it is on the CPU or the GPU. Now, the very interesting thing is that I can very simply just place any tensor I have very simply on the GPU. So here, let's make a fresh tensor here, zeros again of size 10. And then simply I can say x equals x.CUDA. This is just going to place the tensor on the GPU for me. The very first instance, it's going to have to load CUDA, so it might take a few seconds, but after that, everything is going to be much, much faster because you're accelerating your operations on the GPU. So here I have x plus 2, and you can see that the device type is CUDA, and it's the 0th GPU I'm using there. So very simply, I can put things back on the CPU in case I need it. For example, if I'm I/O bound or I need a certain operation to be performed on the CPU, I can just again do x.cpu, and if I look at the device again, you see that it is on the CPU. So PyTorch is offering us a lot of the capabilities that NumPy offers, but the cool thing is that it is very easily available to be placed on the GPU, and of course there are lots of other functionalities that PyTorch offers us that makes this very helpful. So I hope you've learned something, and thank you very much.